Hey everyone, and welcome to this explainer. Today, we aren't just going to be looking at dry numbers on a chalkboard. We are diving headfirst into a high-stakes, 2,000-year-old battle of hidden messages. It's the absolutely fascinating math of secrets.
Think about this for a second. If ancient emperors and modern hackers both use math to hide their most valuable secrets, why do the hackers almost always win? It's a pretty crazy question, right? But it sets the perfect stage for our journey today. We're going to trace the evolution of secret codes, starting all the way back on the battlefields of ancient Rome, straight through to our modern digital age. We'll look at the core problem of keeping data safe, exactly why those ancient methods fail so spectacularly today, and the brilliant mathematical solutions that are literally protecting our digital lives right now. Okay, let's dive into this. At its absolute core, what really is cryptography? Well, the ultimate goal is to encode an algorithm so that your message looks like a complete junk pile of random numbers to anyone snooping around, but makes perfect, crystal clear sense to the intended receiver. It relies on a carefully constructed illusion of chaos. You basically need two things: an encoding algorithm to scramble the data up, and, crucially, a secret inverse decoding algorithm that untangles that exact mess.
All right, let's jump right into Section 1, Caesar Cipher, breaking the code. Now, what's really interesting about this slide is how beautifully simple this first encryption method actually is. We're starting with a method famously used by Julius Caesar over 2,000 years ago to send secure military commands to his generals. The absolute easiest way to hide a word is to just substitute the alphabet with integers. A becomes 1, B is 2, all the way down to Z is 26. This conversion table is the foundation of the whole cipher. It takes human language, which is super easy to read, and turns it into numbers, which are super easy to manipulate mathematically.
Let's actually make this math interactive and walk through the exact steps together. Imagine we want to encode the name James. Step 1, we use our handy table to convert it to numbers. So J is 10, A is 1, M is 13, E is 5, and S is 19. Step 2, we apply a secret shift algorithm. Let's just say we agree to add 8 to every single number. Finally, step 3 gives us our newly scrambled result: 18, 9, 21, 13, and 1. If we turn those numbers back into letters, we get summa. This is utter nonsense to anyone who intercepts the message but doesn't know our secret shift.
And here is the exact mathematical formula behind the scramble we just did. X goes to x plus 8 modulo 26. Every single letter basically just shifts forward by exactly 8 spaces. To decode it, the receiver simply does the exact inverse. They just subtract 8. It's simple, it's elegant, and for a very long time in history, it was incredibly effective on the battlefield.
But here is exactly why these old methods are absolutely no longer sufficient for today. When we analyze the Caesar Cipher from a modern perspective, it exposes a fatal security limitation. There are only 26 possible shifts in the English alphabet. A modern computer? It can brute force all 26 possibilities in a fraction of a millisecond. It literally just tries shift 1, then shift 2, then shift 3, until recognizable English words pop out. That's exactly why we had to evolve to systems like modern RSA, which relies on massive prime factorizations that are mathematically secure against that kind of brute force.
Moving right along to Section 2, Modulo, the math engine.
So, the crucial point is, to understand how we actually achieve modern digital security, we need to meet the real hero of our story, modulo. So what does that actually mean? Congruence modulo M happens when two numbers, let's call them A and B, leave the exact same remainder when you divide them by M. Just think of it as clock math. If it's 10 a.m. right now, and you add 4 hours, it's not 14 o'clock, right? It's 2 p.m. The numbers hit a ceiling and just wrap back around. In cryptography, this modulo acts as a continuous scrambling loop that keeps numbers from getting infinitely large while still mixing them up completely. And you know, this modulo arithmetic isn't just some abstract textbook theory. It quietly serves as a foundation for our daily lives. Take a look at these practical uses. When you're buying groceries, that 12-digit UPC barcode uses modulo math on the final check digit to immediately catch if the scanner misread a line. It verifies ISBN numbers on the books you buy. And most importantly, it is the bedrock protocol for securing credit card transactions. Every single time you tap to pay, modulo arithmetic is working away in the background to verify that data.
Which brings us to Section 3, Digital Locks, Building Security.
Now we're going to shift gears to see how this math engine is weaponized for good. The evolution of this field is honestly cinematic. We start way back in 50 BC with Caesar's simple shift cipher. Fast forward over a millennia to the 1700s, and a Swiss mathematician named Leonhard Euler introduces the phi function, a brilliant leap forward in number theory. But the real game changer? That happens in 1977. Three researchers at MIT, Rivest, Shamir, and Adleman, combined Euler's math with modern computing to describe the RSA protocol. That single massive breakthrough is what secures almost all electronic commerce today.
Let's move to and see how this builds in practice. The secret sauce of RSA is picking two prime numbers, let's just call them P and Q, and multiplying them together. By applying Euler's theorem and that modulo clock math we just learned about, they create a brilliant one-way mathematical lock. You can easily encode a message using the resulting public key, but you can only decode it if you know the two original completely hidden prime numbers.
Let's look at this mini-story of Alice and Ben to make sense of it. Alice wants to send the secret letter M to Ben. M is the 13th letter of the alphabet, so her starting number is 13. Ben has publicly shared his encryption lock, the numbers 899 and 31. Alice's computer takes her 13, raises it to the power of 31, and applies modulo 899. The result is 602. She sends 602 across the open internet. Any hacker intercepting this just sees a totally useless number. But Ben has the private key, the exact reverse modulo formula. He plugs in 602 and out pops the number 13. Boom, he knows she meant M.
All right, Section 4, Power of Primes, Immune to Brute Force. So why exactly does this work so incredibly well? The entire RSA secret really boils down to this. To break the code, a hacker absolutely must know how that final large number n is factorized into its two original primes, P and Q. The brilliant trap here is that multiplying two massive prime numbers together takes a computer a fraction of a millisecond. It's super fast, but working backwards, taking that massive resulting number and untangling it to find the two original primes, that is incredibly, almost impossibly hard.
And this brilliantly illustrates why modern computing power can't just break this cipher. Today, the prime numbers used in secure cryptography aren't small, they are absolutely massive. We are talking about prime numbers that are over 200 digits long. If you tried to have a supercomputer guess the prime factors of a number that size, it could literally take longer than the current age of the universe.
In fact, the math is so overwhelmingly difficult that there are massive real-world cash bounties out there right now. Researchers have offered up to $50,000 to anyone who can successfully factorize specific 200-plus digit RSA challenge numbers. That's how confident mathematicians are in this lock. It raises the stakes and proves that we are finally mathematically secure against the very brute force that completely broke the ancient ciphers.
And finally, Section 5, Math Explorers. Join the community.
We've covered an incredible amount of ground today, highlighting the invisible mathematical architecture of our reality. If you want to keep exploring the deep logic that powers our modern world, we absolutely want you to join us. Be sure to subscribe right here on the Robo for Education YouTube channel for weekly deep dives into the math that actually matters. Make sure you follow our site, blog, and social accounts for interactive tools and daily puzzles. And definitely don't miss out. Join our Google Chat Place. It's a super vibrant hub where you can chat with fellow math explorers, ask questions, and collaborate on all these mind-bending concepts. I'll leave you with this final provocative thought. Now that you know how a 300-year-old mathematical quirk like modulo arithmetic is actively protecting your credit card right this very second, you really have to ask yourself, what other ancient mathematical secrets are quietly running your digital life today? Keep questioning, keep exploring the numbers around you, and I will see you in the next explainer.